In this problem, we want to graph the function 2x plus 1 over x. And we want to sketch it using all of the concepts of derivatives, x-intercepts, y-intercepts, all of that. Concave up, concave down, and inflection points. We want to go from start to finish here. So a good starting point would be to just identify any sort of intercepts. So x-intercepts, y-intercepts. X-intercept is when we cross the x-axis. So what does that mean for x-intercept? That means that we want when y is equal to 0. So we want to cross the x-axis. So that's when y is equal to 0. So we're going to set this equal to 0. So 2x plus 1 over 0. I'm sorry. Over x. 0. So then that's going to give us 2x plus 1 equal to 0. Subtract 1, divide by 2. So we get x equals negative 1/2. So negative 1/2, 0 is going to be our x-intercept. So we can go ahead and throw that onto the graph. Intercept 0 there. Next, y-intercept. Y-intercept is going to be when x is equal to 0, right? Because here's the y-axis. When we cross that y-axis, that means our x value is 0. So all I'm going to do is just change everywhere where I see an x and replace that with 0. So 2 times 0 plus 1 over 0. So since we have this 1 over 0, that means that we have no y-intercepts. And that's kind of weird, but when we look at the next step here, it'll make a lot more sense. So the next step would be to identify any sort of asymptotes. So let's look at vertical asymptotes first. So vertical asymptote is when we can zero out the denominator, and we don't want to zero out the denominator, so what values would zero out the denominator? In this case, when x is equal to 0. So x cannot equal 0, so at 0 we have a vertical asymptote. So vertical asymptote at x equal to 0. So x cannot equal 0 because that would make 0 in the denominator. So therefore is a vertical asymptote at x equals 0. That's why we don't have a y-intercept. Because the y-axis is an asymptote in this case, because x equals to 0. And then horizontal asymptotes. Let's go to our function. Look at the degrees. So the exponents here on the x to the first, same degree. So since we have the same degree, we just take that coefficient of y equals 2 over 1, coefficients, 2 over 1, so 2x over 1x, same degree, so it's just 2 over 1, which is just going to be 2. So that means we have a horizontal asymptote at y equal to 2. Horizontal asymptote at y equal to 2. This is a good check. You see where we have this x-intercept? This should give me a decent idea of what might be happening here. Like, I think, based off of that intercept, that something like this is going to be happening. I don't have any slant asymptotes or any other asymptotes other than this. So just going off of, like, okay, here's what I think might happen. Just because I have that intercept there. So that's indicating to me that something's might be happening there. Okay, next step would be to take some derivatives. So we have the function 2x plus 1 over x. And we need to take some derivatives. The easier way would just be to do this. So change the function to 2x over x plus 1 over x, making that 2 plus 1 over x. So there is another way of using the quotient rule. That gets pretty complicated pretty quick. Derivative of the top is 2 times x minus. It's not like super complicated, but it's just a lot more work than just doing this, right? Because if we take the derivative now, so let's take the derivative. What's the derivative of 2? 0. And then we just have 1 over x. What's the derivative of 1 over x? And that might be something that you've done a lot. I'm going to just do this off to the side over here. So 1 over x is x to the negative 1. So the derivative is negative 1 x to the negative 2. So subtract 1. Negative 1 times 1 is negative 1. Negative 1 minus 1 is negative 2. So that becomes negative 1 over x squared. So the first derivative is negative 1 over x squared. I think that was a little bit easier than quotient rule, personally. But you could use quotient rule. It's perfectly fine. Let's go ahead and knock out the second derivative. So working from here, second derivative is going to be negative 2 times negative 1, which is a positive 2. X, and then we subtract 1. Negative 2 minus 1 is a negative 3. So positive 2 over x to the third for our second derivative. All right, moving right along here. Let's see, what else can we do? So from here, we can try to identify some critical values. So that's taking the first derivative, setting it equal to 0. Oh, while I'm thinking of it, so we're thinking about critical values, let's go back and talk about domain. I should have talked about domain when I was talking about the asymptotes. So the asymptotes were x equal to 0, y equal to 2. So the domain is going to go from negative infinity to 0 and 0 to infinity. So it's going to go from negative infinity to 0 and then from 0 to infinity. So it exists everywhere besides at 0. So just something to keep in mind when we're talking about domain. We always want to be aware of the domain of our functions. So the critical value, so when the derivative is equal to 0, take our first derivative, which we got right here, negative 1 over x squared equal to 0. Can't solve that, so we have no critical values. But domain, we want to know, is it increasing, decreasing, going up to 0, increasing, decreasing, coming on the other side of 0? So we want to take those intervals that we just created with the domain, negative infinity to 0 and 0 to infinity. We want to test some points in the first derivative. So f prime of, unfortunately, 0 is that dividing line, so we can't use 0. And then f prime of positive 1. So plugging in negative 1 into the first derivative is going to be negative 1 over the negative 1 squared is positive 1. Negative over a positive is a negative. So that one's going to be decreasing. Here, positive 1 squared is positive. Negative over positive is negative. It's also going to be decreasing. So we got two intervals that are decreasing. All right. Move me. Yeah, quite a process. Not even out of the woods yet. So now we have to determine if there's any sort of inflection point. So we want to take our second derivative, set it equal to 0. So our second derivative came out to be 2 over x to the third equal to 0. Same thing happens as the critical value, so no inflection points. But we want to do the same thing and identify concave up, concave down. So negative infinity to 0. And then from 0 to infinity. So from negative infinity to 0, we want to use a test point. So f double prime of negative 1. And then f double prime of positive 1. So f double prime of negative 1 is into the second derivative now. So negative 1 to the third is negative. 2 over a negative is a negative. So that means we're going to have concave down. Double prime of 1. So 2 over 1 is positive. So that means we're going to have concave up. All right. And just to save us a little bit of time here, you could get some x values and get a really precise looking graph, but just to not extend this out any longer than it needs to be, I'm going to go ahead and just take our information and throw it onto the graph. So what we have here is from negative infinity to 0, we have that it is decreasing and it's concave down. So since it's decreasing, concave down, it is going to look like this. I'm going to use this x-intercept here as a little bit of a guide. So it's going to do something like this. I missed it. Sorry. I should have done like that. Just missed it a little bit. That's okay. It's hard to be super precise with the tablet. So that's about as close as I can get. And then what we know on the other side of that asymptote is 0 to infinity. We have decreasing, concave up. Decreasing, concave up. So that is going to look like this. So something like that. It's decreasing, it's concave up. It's decreasing, concave down. There's our graph. And we have our intercepts identified. We have all of our asymptotes identified. And that would be it.